Assalamu alaikum. Let's start with the topic of flip-flops. We can explain it. The state of a latch or a flip-flop is mostly switched or changed by the change in the control input or enable input. This momentary change is called triggering, and the transition it causes is set to trigger the flip flops. In the case of D latch flip flops, if we uses the pulses at the control input or enable input, then it is converted to a flip flop that is triggered every time the pulse goes to the logic level 1. So as long as the pulse input or control input or enable input remains at this level, any change in the data input will change the output and the state of the latch. So we can see this is the clock response in the case of latches. If these are the states, we can say this is the level 0 and this is the level 1. So until and unless this clock pulse remains at this level of 1, if the circuit or latch is a positive uh, edge triggered, then at this level of the control signal or enable input, the data input will be transferred to the output uh, until and unless the state of this pulse or control signal is changed from this high level to the low level. So then data will be received, paused, and it will wait to for the next clock pulse to occur. And when the next time clock pulse uh, goes to the logic 1 or high level, the latch will again start to transmit the data from input to the output. So as in the case of D latches, we can see as in our last lecture, the latches will respond to the new values and new output states only when the control input or the enable clock pulse is at the logic level 1. So the result is an unpredictable situation since the state of the latches may keep changing as far as long the clock pulse stays at the active level. Because of this unreliable operation, the output of a latch cannot be applied directly or through combinational logic to the input of the same or another latch when all the latches are triggered by a common clock source. So, in the case of flip-flop, circuits are constructed in such a way as to make them operate properly when they are a part of a sequential circuit that employs a common clock. So, the problem with the latch is that it responds to a change in the level of a clock pulse. As we can see in this figure, that a positive level response in the enable input allows the changes in the output when D input changes while the clock pulse stays at logic level 1. And the key to the proper operation of a flip-flop is to trigger it only during a signal transition, that when signal transition occurs. This can be accomplished by eliminating the feedback path that is inherent in the operation of sequential circuit using latches. A clock pulse goes through two transitions, we can say from 0 to 1 and from 1 to 0. The positive transition is defined as the positive edge and the negative transition is defined as a negative edge. Uh, so there are two ways that a latch can be modified to form a flip-flop. One way is to employ two latches in a special configuration that isolates the output of the flip-flop and prevents it from being affected while the input to the flip-flop is changing. Another way is to produce a flip-flop that triggers only during a signal transition from 0 to 1 or from 1 to 0 of the synchronizing signal or clock input and is disabled during the rest of the clock pulse. So we we can proceed that how the implementation of the both types of flip-flops can be uh, considered. So let's see that how edge triggered D flip-flops works. They are so here in this figure you can see the construction of a D flip-flop with two D latches and an inverter is as we can see in this diagram. The first latch, we can say the first D latch is known as the master latch, and the second one is known as the slave latch. So this kind of flip flops are also known as master slave flip flops. So the circuit samples the D input and changes its output Q only at the negative edge of the synchronizing or controlling clock designated as the CLK, as we can see here, CL clock signal. When the clock is 0, the output of the inverter is 1. This inverter, the slave latch is will be enabled at the time when the clock is 0, and because of this inverter this here will be 1 and slave latch will be enabled, and its output Q is equal to the master output Y. The master latch is disabled because clock signal is 0, and this master latch is disabled. So when master latch is disabled, the our data from the um, clock signal, because of the zero state of the clock signal, and when the input pulse changes to the logic level 1, the data from the external D input are transferred to the master. So the slave, however, is disabled as long as the clock remains at the level of 1. So we can see here when clock signal is at positive or at level of 1, this master latch or D latch, master D latch will be enabled, and data from the data input D will be transferred to the its output Y, and it will be transmitted as soon as until and unless the clock signal is at the level of 1. And when clock goes from 1 to 0, this master latch or master D latch is disabled, and because of this inverter the slave latch is enabled, and data at the output of the master latch is transferred to the output of the slave latch, and output is obtained, we can see in this. So these this is the because it's enabling it is enabled because of the 0 at the clock signal. So any change in the input changes the master output when the clock signal is at the level of 1, and but cannot affect the slave output until and unless the clock signal goes from 1 to 0. And so when pulse returns to 0, master is disabled and is isolated from the D input, and at the same time slave is enabled and the value of the Y is transferred to the output of the flip-flop at Q. So a change in the output of flip-flop can be triggered only by and during the transition of the clock from 1 to 0, when clock signal is changes. The behavior of master slave flip flop, just as we have discussed here, it tells us that the output may change only once, and a change in the and a change in the output is triggered by the negative edge of the clock, and the change may occur only during the clock's negative cycle. These are the uh, two things that first latch is called the as we say has seen master and second is slave, and at the negative edge of the controlling clock the data is transmitted from the master's output to the slave's output. So these the value that is produced at the output of the flip-flop is the value that was stored in the master state immediately before the negative edge occurred. It is also possible to design such a circuit so that the flip-flop output changes on the positive edge of the clock. This happens in a flip-flop that has an additional inverter between the clock terminal and the junction between the other inverter and input, and we can say enable input or control input of the master latch. Such a flip-flop is triggered with a negative pulse so that the negative edge of the clock affects the master and the positive edge then will affect the slave and output terminals. So we can change these two different types as we have seen these clock responses in the flip-flop that these can be positive edge and there can be a positive edge response and a negative edge response. So in the case of positive edge response, transition will be occur when it goes from 0 to 1, and in the case of negative edge response, transition will occur when it goes from 1 to 0. So these are the two we can say responses of in the case of flip-flops. If we see that D-type positive edge triggered flip-flop, it uses three SR latches as we can see in this uh, diagram figure. One, two, and these are the three SR latches are used in the case of D-type positive edge triggered flip-flop. Two latches respond to the external D data input. As you can see that the first parallel SR latches respond to the D data input and the clock inputs. The third latch provides the outputs for the flip-flops. You can say this in the SR latch will provide the outputs for the flip-flop. The S and R inputs of the output latch, these S and R inputs of the output latch are maintained at logic 1 level when clock is 0. This causes the output to remain in its present state. Input D may be equal to 0 or 1 if D is 0 when clock becomes 1, R changes to 0, and this causes the flip-flop to go to the reset state making Q 0. If there is a change in the D input while clock signal is at the state of high level or 1, terminal R reset inputs remains at 0 because Q is 0. Thus, flip-flop is locked out and is unresponsive to further changes in the input when the clock returns to 0, and when R goes to 1, placing the output latch in the quiescent condition without changing the output. Similarly, if D is equal to 1 when clock goes to 0 to 1, S will change to 0, and this will cause the circuit to go to the set state making output Q is 1. Any change in the D while clock is at the state of 1 does not affect the output in the case. So in this diagram, we have described that how D-type positive edge triggered flip-flop works. These are the graphic symbol for edge triggered D flip-flop, and we can see here in this positive edge triggered D flip-flop, mm, we can that here is a D input and a control input, and there are two outputs with Q and Q prime. Q prime is with the bubble sign at its output outside the square. In when a input clock in the positive edge triggered flip flop makes a positive transition, the value of D is transferred to Q, and in the negative transition of the clock, that is from 1 to 0, does not affect the output, nor is the output affected by the changes in the D when clock is in the state of logic 1 level or the logic 0 level. Hence, this type of flip flop responds to the transition from 0 to 1 and nothing else. So we can see that this type of D type positive edge triggered flip flop will only trigger or transition or change its states during the cycle of when its control input changes from 0 to 1 and nothing else states. So the timing of the response of a flip flop to input data into the clock must be taken into consideration when one is using edge-triggered flip-flops. There is a minimum time called the setup time during which the D input must be maintained at a constant value prior to the occurrence of the clock transition. Similarly, there is a minimum time called the hold time during which the D input must not change after the application of the positive transition of the clock. So when clock signal occurs, the D input is hold, we can say, and the output will be according to the D signal, and that time is called the hold time. And propagation delay time of the flip flop is defined as the interval between the, we can say, trigger edge and the stabilization of the output to a new state. These are the parameters specified by the different manufacturers in different data books. As from these graphic symbols, we can clearly see that this D shows the data input, C shows the control signal, and bubble shows that this is a complemented output Q prime, and this is a Q output. Bubble outside the block adjacent to the dynamic indicator designates a negative edge for the triggering circuit. As this bubble shows a negative for negative edge for triggering the circuit. In the absence of the bubble designates a positive edge response. As it's the absent bubble, so it shows a positive edge response, and with the presence of this edge, it shows the negative edge response in the edge triggered D flip flop. And there are other different other types of flip flops which are also known as JK flip flops and perform with a, we can say, set it to 1 and reset it to 0 or complement its outputs. The JK flip flops performed all three operations of the, we can say, set reset. The circuit diagram you can see here constructed with the D flip flop and the two AND gates and an OR gate and an inverter using the inputs known as which are J and K inputs. So in this case of we can say JK flip flop, the D input which is at this point will be equal to the J Q prime plus K prime into Q, and by when the value of j is equal to 1 and k is equal to 0, d will j is equal to 1 and k is equal to 0, then d will be equal to q prime plus q, and which will be equal to 1. We can use annotations here, and if we say j is equal to 1 and k is equal to 0, then its complement will be equal to 1. So the output will be, or we can say the D input will be equal to Q prime plus equal to 1. So the next clock edge sets the output to 1 when j is equal to 0 and k is equal to 1. D will be equal to 0 in that case. So next clock edge resets the output to 0. When both j and k are 1 and d will be equal to q prime, the next clock edge complements the output when both the j and k are 0 and d will be equal to the q out. The clock edge leaves the output unchanged. The graphic symbol for the JK flip-flop we can see here in this diagram, and the its characteristic table as when J and K both are 0, no change will be occurred. We can say that the output will be Q, and when J is equal to 0 and K will be equal to 1, it will be at the reset state, and when J is 1 and K is 0, it will be at the set state, and for both, when both the inputs J and K are 1, 1, it will be a complement states. We can say the output Q prime will be occurred as we can see here. So this was the JK flip flop which is used here, which uses a D flip flop and two AND gate with a OR gate and an inverter to establish the function of the flip flop. And other is a kind of flip flop is a T flip flop. It uses T is stand for toggle flip flop is a complementing flip flop and can be obtained from a JK flip flop when inputs J and K are tied together. So that's why uh, the toggle flip flop or T flip flop is a complementing flip flop, and by combining both the inputs J and K, we can obtain this T flip flop from the JK flip flop as shown in this block diagram of the T flip flop. It's the characteristic table of the D flip flop, and the D flip flop can be constructed with a D flip flop and an exclusive OR gates, uh, as we can see in this figure. That D will be equal to T exclusive Q. D will be equal to T exclusive this Q signal, and we can use the annotations here, and it is the Q output which is feedback to the input of the exclusive OR gate. So this will be equal to the this output of exclusive OR will be P exclusive Q. And we can open this statement, and also we can say that when T is equal to 0, the D will be equal to Q, and there is no change in the output when T uh, and when T changes from 0 to 1, D will be equal to Q complement, and the output will be complement, and the graphic symbol is shown here with D input and a control input and output of the two outputs of Q and Q complement. So this was the T flip flop, which is you can say constructed with the help of a D flip flop, and we can these are the we can say generalized characteristic equations of different flip flops. We can say for the D flip flop, D is equal to Q. The output So for the next state will be equal to the D, and for the case of JK flip-flop characteristic equation, next state will be equal to the J Q complement plus K complement into Q, and for the case of the T flip-flop, the next state, or we can say the output equation, which will be equal to the T exclusive Q. Mm, Q. These are the characteristic equations which are used in these three flip-flops, D flip-flop, JK flip-flop, and T flip-flops. Uh, so, inshallah, in our next lecture, we will see about the that analysis of the clock sequential circuits, state equations, and how the state diagrams are made. So in this, at the end, we see that some flip-flops have asynchronous inputs that are used to force a flip-flop to a particular state independent of the clock. The input that sets the flip-flop to one is called the present or direct set. The input that clears the flip-flop to zero is called the clear or direct reset input. When power is turned on a digital system, the state of the flip-flop is unknown, as we have already discussed. So the direct inputs are useful for bringing all flip-flops in the system to a known starting state prior to the clock operation. So inshallah, our next lecture we will see about the state equation, state diagram. So take care, students. Allah Hafiz. Assalamu alaikum.